All right, so yesterday we finished up practicing measurements and including the proper number of digits. Let's practice with 5, 6, and 7. Let's do 8 and 9, but skip 10 and 11 for now. We'll come back to that and do that as a class. So what I would do is work on 5 through 9 with a partner. Make sure you're getting similar answers. Most importantly, you want the same number of digits. So check with your neighbor once you think you've got it. All right, let's go through this as a class in case a few of you are stuck. So on number 5, it looks like we've got hash marks for the tenths place, right? So what should we estimate out to? The hundreds. And then this one, I would say that line looks like it's smack dab on the middle of 16, so what might our best answer be? 16.00. Sure. We'll do that, and we'll say 16.00 centimeters, and in this case, we were estimating that last digit, which is now the hundredths place. All right, the next one, it looks like, again, we've got hash marks for the tenths place for problem 6. So we want to estimate out to the hundredths place. Does anybody want to share what they think the answer is for that? What do you think? 12.33. Sure. So we'll write 12.33 centimeters. People will ask, well, I wrote 12.32. Does that mean I'm wrong? No. The whole idea is the last digit's estimated, so it can vary a little bit for that last digit. All right, for the bottom one, again, it looks like we've got tenths place, so we want to estimate out to the hundredths place. So for this one, we could do something like 9 point, I don't know, what do you guys think? 9.40? Okay. So 9.40 centimeters, that sounds good to me. As long as you have the proper number of digits, that's what I'm really looking for. If you wrote 3.54, I might say, yeah, you're not even looking at the ruler right. But as long as you're close and you have the proper number of digits, that's what really matters. All right, for 8, we've got some thermometers. It looks like we've got hash marks for every ones place, so what should we estimate to? The tenths. So for this one, I would say maybe 21.9. It looks like it's not quite at 22. And just like before, we're going to estimate that last digit. All right, the next one, same sort of thing. It looks like we've got hash marks for the ones place. It looks to me like that's right at about 36. So I would say 36.0. We do need to include that 0 to indicate that the hash marks were at the ones place, not anything else. All right, these ones are a little bit weird. Did Adrian talk about these in lab? What do we call this shape? Meniscus, right? Why does it do this? Does anybody know? What do you think?
We talked about it in the lab. It's surface tension.
Surface tension, exactly. So water will actually stick a little bit to glass, which causes it to curve up. That makes measuring in lab a little bit more complicated. Do we want to measure at the top of the curve or the bottom? Yeah, you want to measure at the bottom of the well. So for this next one, we would say, all right, looks like we're in between 4 and 5. The hash marks represent the tenths place. That means we want to go all the way to the hundredths place, right? So for this one, I might say 4.28 milliliters. And we're estimating that hundredths place. But always measure the bottom of that well. All right, the next one, same idea. We're going to measure the bottom of the well. And in this case, it looks like it's right at 30. So would I go ahead and just write 30 milliliters? No, what else should I do? 30.0, because we are more confident than that. So we want to say 30.0 milliliters, because we do have hash marks going out to the ones place, right? Okay, so these might show up on exams and quizzes, but most importantly, this is for lab. I have had students ask me, well, what about a digital scale? Do we estimate one digit past the numbers that are shown? No. Yeah, it's a digital scale. Record all the numbers shown and just stop there. That's all you need to do for digital scales. All right. We do have to go over a couple of terminology things. And the first one is accuracy versus precision. And people confuse these a lot and misuse them, even in the media. So we'll start with accuracy. Accuracy means that your data average is close to the correct value. However, are averages really that useful? My example is, if we brought Jeff Bezos into this room, we would all be billionaires. Is that a fair assessment? No. On average, we would be, but that's not a fair representation of the sample. So accurate doesn't necessarily mean a whole lot. The way I like to describe it is, let's say you're at an archery range or a shooting range, and you've got a target right here. You could be super accurate, even though you're hitting the edges of the target, right? Because the average of all three of these is pretty close to the center. It doesn't mean a whole lot, though. Precision is a little bit different. Precision means that your data is all close together. All right, does that necessarily mean very much? Kind of. Well, let's think about the shooting range analogy or archery range. We could have a target right here, like this. And I could be super precise, but maybe all of my data is clustered off-center like that. Yeah, it's good in some ways, but not good in other ways, right? So on the left, we have something that is accurate. Oh. But not precise. This one is precise, but not accurate. What's the best case scenario? We have something that's both precise and accurate. So in this case, we could draw our last target and we could say, ideally, if you're at an archery range or something like that, you want all of your arrows to hit the center of the target and be clustered together. So this would be precise and accurate. Does that make sense? So accurate, like I said, doesn't always mean a whole lot. It's just playing a game of averages. Precision doesn't mean a whole lot. It just means your data is close together. But maybe your calibration's off. Maybe your scale wasn't calibrated recently. Ideally, you want something that is both precise and accurate. So we will use those terms throughout the term. Any questions? All right, now we've got to get into math rules, because everybody loves math. We're going to talk about significant figures. Has anybody covered significant figures like in high school or another class? A couple people? All right, so this will be new for most people. The question is, when we're measuring things, what digits really matter, which digits don't really matter? So the first thing to remember, it's easy, is that all non-zero numbers are significant. So if I measure something, for example, as 423, how many significant digits or figures are in this? 3, exactly. They're all non-zero, so I just say this has 3 significant figures in it. Pretty simple concept. All right, the second rule, and these all apply, are that all zeros between non-zeros are significant. Okay, so let's take an example of this. Let's say we measure this as 103. This time we do have a 0 in it. However, it's between 2 non-zero numbers, so we still count this 0. So we would count this as still having 3 significant figures. Make sense? All right, rule 3 has to do with decimals. All zeros, this one's a bit longer, which are to the right of a decimal and at the end of a number are significant. So I'll show you an example of this. Let's say we've got 0.00010, and this is our measured value. Rule 3 says that we count the zeros to the right as long as there's a decimal, right? So in this case, this zero's to the right of a decimal. And at the end of a number. That means that this zero at the end is significant. This leads to the other side of this. What about these zeros that come first? Anytime you have a leading zero starting at the beginning of a number, you don't count those ever. So don't count leading zeros. All right, so based on these two rules, how many significant figures are in this measurement? 2, exactly. We don't count the leading ones, but we do count the one to the right because there is a decimal in this case. So this would have 2 significant figures. All right, one last rule to make things more complicated. Says that all zeros left of a decimal and in a number greater than 10, actually greater than or equal to 10, are significant. So I'll show you an example of this in action. Let's say I have a measurement that is 10.0. Do we count this zero at the end? Yeah, rule 3, right? We said there's a decimal and it's at the end of a number, so we do count this. So I would say this is right of a decimal, so this is rule 3. So I'll just write this down to keep track of everything. And then this one over here is left of a decimal and in a number greater than 10. So we also count that one, right? So this would be rule 4. All right, so if we think about this one, we do count both of those zeros, so this would have 3 total significant figures. All right, let's try a harder one, though. Let's do 1,000. How many significant figures do you think we have for 1,000? It's a little bit weird to think about, but let's go back and reread Rule 4. Rule 4, I said all zeros left of a decimal and in a number greater than 10 are significant. Do we have a decimal here? Not one shown. So we don't count these zeros because no decimal is shown. It's a little bit weird. So we'll say don't count. There is no decimal. Okay, so this one would just have 1 significant figure. All right, just to make things more complicated, What happens if you see 1,000 written with a decimal? What do you think? Yeah, now you count those zeros. So it's a little bit weird. You have to pay really attention to whether or not a decimal is shown or not shown. So in this case, we would count all of those, and this would be 4 significant digits. The 1 counts and all 3 of those zeros count because they're to the left of a decimal. Make sense? All right, so let's do a few practice ones. So I'll put a number, and then I want you to predict the number of sig figs. So first number is 48923. Next one, I'll do 3.967. Then I'll do 900.06. Then I'll do 0.0004. Do 8.1000. And then I'll do 501.040. So I'll give you a minute to work on this, but check with your neighbor. All right, let's try to do this as a class. The first one I think is pretty easy. We don't even have zeros in there. So how many sig figs should we have? 5. We want to count all of them as significant, so I'll just say 5. What about the next one? 4. We don't even have zeros. That one's easy. All right, the next one's a little different. We do have zeros. Do we count those, though? Yeah, why? Yeah, they're in between 2 non-zero numbers. That was rule 2. So we count all of these, so this one would also be 5. All right, next one's a little bit different. Do we count the zeros for this one? Why not? Because they're leading zeros, right? We never count leading zeros. Okay, so this one would just have 1 significant figure. All right, the next one, we do have zeros to the right. Do we count those? Yes, we have a decimal, therefore we count the right zeros. Okay, so this one would also have 5. And then the last one's the hardest. We've got a bunch of different types of zeros. Are we going to count all of these zeros? Well, let's think about this one, right? Do we count the first zero between the 5 and the 1? Yeah, it's between 2 non-zeros. What about this one? I would say we do. It's between 2 non-zeros, so we count that one. What about the one at the far end? It's to the right of a decimal. So we count all of the zeros in this example, so this one actually has 6 significant figures. It is a little tricky to remember these rules, so try to practice as much as possible. Yep.
Are they only considered leading zeros when there's a zero in the tens place?
They're only considered leading zeros if they're at the beginning of a number, so at the start. So all of these were leading because they were at the left. Does that make sense?
Yeah, I was just like the difference between that one and the one before it, because the zero after.
So this one?
Yeah, so like the zero after the decimal did count for that one, and then they didn't count for the
Yeah, so this one, the reason we count these zeros is because they're in between non-zeros. Does that make sense? Yeah. It is confusing. There are a lot of rules to remember, so just try to practice these as much as possible. Ideally, on an exam, these are freebie points, but you got to know the rules. All right. Significant figures are really important, and I did want to make a note why. Significant figures are important for measured values. Why do you think it's important for measured values but not just generic numbers? Think about the worksheet that we were just doing. What does it indicate? So we saw the more decimals you have, if you're going out to the tenths or hundredths place or even further, that means you've got a really accurate measuring tool, right? Something that's very, very certain. So it gives you the degree of certainty. And remember, your last digit is estimated. So that's the key thing with significant figures. If I just give you a generic math problem like 5 times 5, you don't need to worry about significant figures because that's an abstract thing, not something you're measuring, right? It's just telling you 5 times 5. All right. There will be situations where you have to do math with significant figures, so we'll go over some of the rules with that. And the math rules are also a little bit strange and sometimes don't make a lot of sense, but bear with me. We'll do addition and subtraction first. I'll give you the definition of the rule, and then what we'll do is we'll show it with an example. It makes a lot more sense when you see an example. So the rule for addition and subtraction is your results cannot be more precise than your least precise measurement. Okay, so I'll show you an example of this. And in this example, let's say I measured a few different values. My first value I measured to be 23.112233 meters. That's my first value I measured. My second value, I'm going to stack below, and I'll say 1.3324 meters. And then last but not least, my third value that I measured was 0.25 meters. I like to stack them this way, so kind of old school addition subtraction. And then what you do is put your cross underneath, and in this case we're going to add them. However, the same rules apply to subtraction. Okay, so we can go in and plug this into our calculator, no problem. And the answer, I believe, you can check me on this, should be 24.694633. Is that right? I think so. Yeah, that looks right. And then what we want to do is first identify our least precise measurement. Is our least precise measurement the first one, second one, or the third one in the stack? Third one. It's only precise out to the hundredths place. So immediately what I like to do is kind of say, well, we can't be more precise than the hundredths place, so I'll put this kind of red dotted line through there. That means that my final answer is going to be 24.69 meters, not that big number, right? So we'll cross these out. We'll say it is 24.69 meters. Same rule for subtraction as well. So if we were doing subtraction, you would say this is only precise to the hundredths place. We can't assume anything beyond that. Does that make sense? All right, multiplication and division are a little bit different. And the rule for multiplication and division is that your results cannot have more sig figs than your number with the fewest sig figs. Your number with the fewest sig figs. And again, this makes a lot more sense when you do an example. So for my example, I'll do, let's see, 23.123123 meters times 1.3344 meters. You can go ahead and plug this into my calculator, and the answer I get before doing sig fig manipulation is 30.855. I think it's 495 after that. And then I think it's 3315. All right, what would my units be for this? This one's a little harder. It'd be meters squared, right? So you do have to multiply the units together too. So we would show this as meters squared. Be kind of like measuring a room, right? You can measure feet going one way, feet going the other way, and then measure the room by square footage. We're measuring this room by meters squared because that's a scientific notation. All right, first thing I do anytime I'm looking at multiplication or division is assess the significant figures. How many significant figures do we have for this first number? 8. Okay, so we've got 8 sig figs. It's not too bad. We don't even have a 0 in there. All right, same thing with this one. Looks like we only have 5 sig figs here. All right, which means our final answer can only have 8 or 5 sig figs. 5. Okay, so we go ahead and we'd say, all right, these numbers matter, these numbers don't. So our final answer would be 30.855 meters squared. This would be the best answer for that multiplication. Does that make sense? All right, let's do another weird example. This one drives people nuts. Let's do 5 meters times 5 meters. Hopefully you don't need a calculator for this one. If you type this in though, what would the correct answer be? 25 meters squared. All right, but let's go back and assess significant figures, right? If we look at the first one, how many sig figs do we have? 1. All right, and then over here, we also have 1. How many sig figs should we have for our final answer? 1, but we have 2. So then the question is, all right, we would look at this one. This one has 2 sig figs, but if you notice up here, I'm going to highlight it. The digit immediately following was less than 5, so we didn't have to worry about rounding up. We just rounded down. In this case, are we going to round up or round down? We're going to round up because it's 5. So if you remember basic rounding rules for math, if it's 5 or larger immediately following your last sig fig, you round up. Otherwise, keep it the same. Okay, so the correct answer for this one should be what? Yeah, 30 meters squared. This drives people nuts, right? Because they're like, well, what do you mean? 5 times 5 is 25, not 30. I'd say not in chemistry, you're measuring these. Basically, another way of thinking about this is imagine going out and you're looking at boards, right? You're saying, it's about 5 feet by 5 feet. We should probably buy about 30 meters squared of flooring, right? It's just an estimating tool because we're estimating the ones place and the 5s, right? So we have to be incredibly careful with our sig figs. The other thing to remember is if you write this as 30 with a decimal, is that right? No, that has 2 sig figs, so we couldn't write it that way. That wouldn't work. However, what we could do is we could write 3 times 10 to the 1 meters squared. Either one of these would work as our correct answer because they both have 1 sig fig, right? Some students get confused too and they say, well, why don't you count the 10 as included in the sig figs? We just don't. Anytime you've got scientific notation, don't include the 10 raised to whatever power. That's not significant. It just tells you the order of magnitude. Does that make sense? All right. Going off this same example, let's say I'm being more careful with my measurements and I pull out a tape measure, and now I'm saying it's 5 meters times 5 meters, but it's 5.0 this time rather than just a generic 5. Now what would the area be? 25 meters squared. So in this case, the reason it works out well is we've got 2 sig figs and 2 sig figs, and the final answer has 2 sig figs. So it is really important. Like I said, you only have to worry about this if you're doing math with something that you measured. If you're in a math class, please don't answer 5 times 5 is 30. They'll think you're crazy. This only applies to anything that you're measuring and doing math on. Does that make sense? It's a little bit strange. All right, so we only have a few more minutes. I'll show you a bit of what we're going to cover next week. We're going to be doing a lot of unit conversions. How many of you in your kitchen have had to convert between like tablespoons and cups? Essentially, that's what we're going to be practicing, is how to set up the math for that. But I did want to do a few generic examples to warm up. So we might need that sheet again. But let's do an easy warm-up. Let's say we have 2 dozen eggs. And the question is, how many total eggs do you have? I know this is advanced math, but off the top of your head, how many eggs would you have? 24, right? It just makes sense to us intuitively. If you were to buy 2 dozen donuts, you'd have 24 donuts as well. But let's try to structure it as a math problem. And in order to do this, we have to have something called a unit conversion to relate dozens to single items. So what I would do is I would write 1 dozen equals 12 eggs, right? Whoop, that's not how you spell eggs. This is going to be my unit conversion for this math problem. And then anytime I start a unit conversion math problem, I always start out with the value that I know. And we know that we're starting with 2 dozen eggs. So I would write 2 dozen. All right. And then what I would do is multiply. And our goal is to cancel out dozen so that our final answer doesn't have dozen as our units, right? We want eggs as our final unit. So should dozen go on the top or the bottom? I would put dozen on the bottom because we know according to our math rules, if you take a number like this, it's going to cancel out the denominator, assuming they're the same. And then we can write eggs on the top. And then if we look back up at this unit conversion, we know that for every 1 dozen, we have 12 eggs. So the 1 goes with the dozen. So it would go down on the bottom. And then 12 would go with the eggs on the top. We have this set up so we can cancel out dozen right here. We can cancel out dozen right here. The remaining unit that's left over is eggs. So this was a lot of math work for something that's relatively simple. And then 2 times 12 over 1 is still going to be 24 eggs. So that would be my final answer. All right, let's go back to the sig fig stuff though. Sometimes students will say, well, we did a multiplication problem here, right? This 2 only has 1 sig fig. Why don't we only have 1 sig fig for our final answer? Does anybody know? Yep.
Is it because there's 12 eggs?
Yeah, it's kind of the unique property of eggs. We don't measure eggs with a yardstick, right? We just physically count them. I don't know how you get half an egg. So in this case, if you're counting something, you don't have to follow the sig fig math rules, but otherwise you do. So for a lot of these, you don't need to worry about sig figs. Just pay attention to whether or not you're measuring something or counting something as a whole number. Does that make sense? Want to try one more warm-up problem before we get into the math? All right. Let's say we've got 144 eggs. and we want to figure out how many dozen we have. Let's try to set it up the same way. So we always start out with what we know, and we know that we've got 144 eggs. We want to multiply times a conversion factor, and this time we want our final answer to be dozens. So should the conversion have eggs on the bottom here or on the top? On the bottom, because we want it to cancel. And then I'll put dozen up here. And just like before, we can go up and look at our conversion factor, and we know 1 should go with the dozen unit. So I'll make sure it's on the top this time, not on the bottom. And then eggs goes on the bottom. So I'll write 12 eggs on the bottom like that. If you noticed, up here we had 12 on the top and 1 on the bottom, but down here, because we flipped our units around, we have to flip the numbers as well. So just like before, we can cancel out eggs. We're left with our desired unit of dozens. And what would our final answer be? 12. I know this seems really simple. The main thing that students mess up on is they either flip the numbers to be upside down, or they flip the units to be upside down. First thing you always want to do is double check that the units are canceling that you want to cancel, and that the units left over are the units you want left over. And then double check that the number corresponds to the correct unit for your conversion factors. Sometimes students just go way too fast through these and they mess them up due to simple errors like that. All right, so next week what we'll do is we'll start doing this with a lot of chemistry-related conversions, and we'll practice that for a day or two. But feel free to email me or stop by my office if you have questions.